In this example, I'm going to consider what happens with a so-called diverging lens, where the object is 5 centimeters away from the lens. The focal length is negative because it's a diverging lens, and it's negative 2 centimeters. And let's just, for illustration, assume that the object has a height or a length of 28 centimeters. So the focal length being negative 2 centimeters, each block here will represent 1 centimeter, so that's consistent. And the object is 5 centimeters away, or 5 blocks, and so I'll indicate it here. I'll sort of draw it like this. And what I'm going to try to do is indicate a height that is a little less than 3 blocks high, and that'll kind of represent the 28 centimeters. The units vertically are different than the units horizontally. The rules for drawing a ray diagram for a diverging lens are sort of the opposite of that for a converging lens. We still have simple rules. We have rays that can come in parallel to the optical axis. And when they hit the lens, what a diverging lens is designed to do is to spread the rays out when they get to the other side. They spread out according to the rule that they move away from the focus that was on the side that they came in from. So the whole construction of this piece of glass or plastic for this diverging lens is designed to do this, to make the real ray go in that direction. We already anticipate that we're going to have to figure out where the virtual rays look like they came from. So let's go ahead and put in a dashed line here, which also will help us make sure that we really have made that ray diverge away from that focal point. So again, the ray comes in and it diverges away from the focus on the same side it came from. Now, a diverging lens, just like a converging lens, has to make sense going forward or backward. So if you think about it, from the other side, if a ray came in, aimed at the focus on the left side, then it would hit the lens and then move on parallel to the optical axis. So let's see what that means. If I aim a ray from the object towards the focus on the other side, we'll try our best here. It would do something like this. Heading towards the focus on the other side, hits the lens, and then it goes on parallel. And you can always double check if this is making sense, because again, this ray should make sense going forward and backward. If the ray was going in this direction, it would hit the lens and diverge away from the focus. What I forgot to do was indicate the virtual ray. Again, that's just the direction from which it appears like that ray came from. Always having in mind that there's some observer who is over here and can tell us, what does it look like is going on here? Where does it look like the ray, the green ray and the yellow ray came from? And they would tell us about the dashed lines, right? They would indicate those are virtual. Now then maybe they wouldn't even know whether or not they were virtual, at least not in any obvious way. But this is going to help us figure out where the image is. We can already see where those dashed lines intersect, about there. Seems like where the image is going to show up. But to be certain, we'll draw one more ray that passes through the center of the diverging lens. Just like for the converging lens, this is designed so that any ray going through the center does not get deflected. I'm trying my best not to cheat. I'm really trying to make a line that goes from the head of the object and goes through the center. And again, somebody would say, this ray looks like it came from back here. But we can see that it really does appear that all three of these rays intersect at that point. That tells us where the head, the arrow on the image is. That's the object. Apparently this is the image. So as far as distances go, it appears to be, well, closer to the lens than the focal length. So focal length of -2. It's going to have to be smaller in magnitude than that. Let's keep in mind that, again, we measure distances positively going this way and negatively going this way. So the image distance has to be negative, but not quite as negative as -2. It kind of looks like perhaps the image distance, let's expect it to be, these are the expectations, maybe around minus 1.5 or so, if we didn't draw this too terribly. We can definitely see the magnification is positive because the image is upright, but it's certainly less than 1, so the expectation is the magnification lies somewhere in here. And anyway, the object height, it's going to be, or the image height is, sorry, that's what I actually mean, the image height. We can have an expectation for what that's going to be. And it's, well, definitely less than 28. It's probably less than half. So I don't know, maybe it's around 10 centimeters or so. That's just a rough guess. So let's actually compute things. We're going to really need to keep track of the fact that the focal length is a negative number. Using our lens equation, let's figure out what is di. We know we can rearrange the lens equation to look like this, 1 over f minus 1 over do. Focal length is negative, so let's write this as 1 over minus 2 centimeters and subtract the object distance, which is 5 centimeters. We could find a common denominator, I suppose. Let's factor out a minus sign. And then the 2 is the same thing as 5 over 10 centimeters. I factored out a minus sign, so that's plus, and that would be 2 over 10 centimeters. So if I haven't screwed this up, which I don't think I have, this should be equal to minus 7 over 10 centimeters, and I have to take the inverse of that, so it would appear that the image distance would be negative 10 over 7 centimeters. That's 1 and a 3/7. So I guess we could just use a calculator for this. 10/7. This is approximately minus 1.4. Okay, so that's actually pretty good compared to our expectations, but that's really what it actually should be. The magnification, we can then go ahead and compute the magnification being hi over ho, which is minus di over do, minus a minus, which is minus 1.4. Why don't we keep that extra digit, 1.43, and I forgot to write centimeters. The object distance was 5. And so the minuses cancel to give me a plus, and divide that by 5, and this is plus 0.286. For magnification, definitely greater than 0 and less than 1, so there's your magnification. And then finally, the image height should be the same as m times ho, in other words, 0.286 times the object height, which I picked 28 centimeters for my object height. And we can multiply that out, and it comes out to be 8 centimeters exactly. And so it's, I think, pretty consistent with that. So there you go. That is a diverging lens. You will find that you always get a virtual image, which this is. You always get a virtual image with a diverging lens. It doesn't matter where you put the object, before or farther away or in front of the focal point. This is in contrast to a converging lens. Sometimes you get a real image, sometimes you get a virtual image. It all depends on where you've put the object relative to the focal point.